Okay, let's get on with Mr. Al-Khalili. And what does Mr. Al-Khalili have to say? Well, he's going to be talking about uh, a very popular subject in the last, I guess, 50 years. It's going to be black holes, dark matter, um, Big Bang, wormholes, parallel universes, parallel realities. So get ready. It's going to be a trip. I mean a trip. Okay, so here we go. Hi, Tesla. Okay, let's get started here. Al-Khalili starts his presentation, his analysis, his actually more a sales pitch. And what he says is the following. He says, science is really becoming part of popular culture. It wasn't that long ago that you would never see a scientist, a physicist, a mathematician standing on stage talking about their worlds, their life, their work, infusing an audience coming from such diverse backgrounds. But science, certainly in the UK now, is becoming very much part of popular culture. Well, the question is whether they're doing science or whether, like I showed there, we have a bunch of clowns, jesters, mimes, stand-up comedians. Is that what they really are, showmen? Is this what these people are? We have Brian Greene there, Neely and Willie Neely, uh, guy with the jester hat. He's Brian Cox, and then good old Al Khalili there. These people are caricatures of science. So the question is, are these people doing science? And let's find out today. We're going to let Al-Khalili tell us about that, okay? I'm going to offer some comments here and there, but we're going to let Al-Khalili talk for them. Are these people doing science? And he starts off on the wrong foot. He says the following. He says, today we're going to find out that fiction is actually science fact. So now fiction has become fact, science. It has become science. So what used to be fiction, you thought it was fiction. No, now it's called science. That's what he's going to argue. Okay, so these are not my words. These are from his presentation. Okay, he didn't say it, but essentially he allowed someone to say it. Like, I agree with him. And one of the fascinating, exciting things about science is that we can tell stories about the most fantastic worlds, about the most improbable and ridiculous ideas that are actually part of our own universe. Does that sound like science or, again, like fiction? What is he doing? Science or fiction? I'm a little lost here. I thought he was going to talk about science and physics, explaining how our universe works, explaining some of the best, most powerful theories in science, how they work, why we trust them, why we believe them, and what they tell us about the universe and our place in the universe. Well, this is strange because as I've been talking the last couple of weeks, the word explain is misused here. They do not explain because they always end their presentations by saying whether they're talking about relativity or quantum mechanics, not to mention string theory. They come in there and they say at the end, right? This is their closing argument. This is their, their summary or their synthesis, right? And what do they say? They say we don't understand it. We cannot visualize it. We cannot imagine it. So what kind of explanation is that? Well, again, it goes back to that word fiction. Oh, if it's fiction, yeah, then it's okay. If you're going to do magic, black magic, is that how you're going to explain that? It's fine. Then no problem. Then please carry on. Okay, but if they're gonna give you nonsense, then it's not an explanation. And this is where we have a problem. What they're doing is not explaining. We don't have a single, listen to this, we don't have a single explanation for any invisible phenomenon of Mother Nature's in mathematical physics today, or in so-called science, which is a synonym of mathematical physics, which is a synonym of math, which is a synonym of experimentation. So this is what they say. They say you do an experiment, you observe, you do the calculation, you measure, whatever, you come up with an equation, that's science. What's the explanation? Oh, we don't know. We don't understand it. So they do not have explanations. That's where the word is misused. I want to highlight that, okay? I want people to understand that these people do not have explanations. Okay, Al-Khalili continues. He says, Newton's theory of gravity, because he's going to be talking essentially, he's going to try to show that gravity is done the relativistic way, not the classical way that started with Newton, or even earlier, you could say with Galileo, or even earlier, who knows. Newton's theory of gravity isn't very accurate. Accurate? A theory being accurate, precise? What are we talking about? Numbers here? Sounds like they're talking about measurement and not about, a theory is objective. It's finished. you finish it, you say, this is the mechanism, we're done. That's a theory. And if he's talking about accuracy and precision, maybe he's talking about something else that has nothing to do with physics or with explaining, with mechanisms. Okay, that's the point. Okay, so his gravity wasn't very accurate. He should have said it's wrong, but he didn't want to say that because that would trash his hero. So he didn't say, well, it's not wrong, it's just not accurate enough. What are they referring to? The fact that with Newton's equation, you could not predict the exact orbit of Mercury around the sun. There was a little difference there, and Einstein he didn't even cover all of it. He covered like halfway. Then they, messed around, they finally got it right. But when Einstein published his theory and the way they all calculated in the 1920s, they said, well, yeah, it's more accurate than Newton's. So we still don't have an accurate theory equation, really, except that they fooled around with it and they're inching it closer to perfection. And again, that's a measurement. It's got nothing to do with a theory. It's not a theory, it's a description. That's what mathematics is. So this idea that we are stuck to the earth because of gravity gives us a picture of an invisible force, an invisible elastic band that pulls objects together. Yeah, that's Newton's, okay? Einstein said, no, there's something deeper about gravity. It has to do with changing the nature of space and time themselves. It curves space, okay? And that's what his general theory of relativity is about. Gravity curves space in a way that is impossible to try to imagine and visualize. So you're not supposed to visualize this. You're not supposed to see the mechanism, visualize the mechanism. In reality, they're going to use an analogy, but they're going to use a three-dimensional analogy to mimic the alleged four-dimensional universe. That's what they're going to try to do. And again, they give that analogy of the flatlander trying to figure out the 3D world. And likewise, we are sort of, these guys are flatlanders, three-dimensional flatlanders trying to figure out the four-dimensional world. And I guess what they're talking about, what Al-Khalili was talking about is this, this warp space thing, okay? We got that famous net. And again, I just published an article in the, I'll put it over here, article in the Quora, and I put this in there. And the issue there, again, if that's the sun there, right, and that net is supposed to represent space and time, we have the 4 dimensions there, two-dimensional, you could say it's a 3-dimensional projection of a net onto a 2-dimensional platform. We cannot imagine the 4-dimension being 4-dimensional object, alleged object, 4 perpendicular directions being projected onto what, a 3-dimensional platform like a hologram or something? Is that what we're talking about here? And so yeah, if that's the net, what's the black stuff that gives shape to the net, that provides background to the net? And the same thing goes even if it's 4-dimensional. Okay, I don't care if it's 4-dimensional and I can't imagine it. Irrelevant. The question is, if it's 4-dimensional, right? A 4-dimensional net, a 4-dimensional canvas, whatever you want to call it, what gives background, what provides background to that 4-dimensional net object or whatever they want to call it? And if they don't have an answer for that, they can't even start their presentation. They have to identify the background. and it's the background that they always have problems with. Okay. Okay, continuing on here. Here we have Al-Khalili, more or less decent. I don't know why I put him so decent in this one, but I want to give him a little bit of credit, maybe. Okay, we live in 3 dimensions of space. Of space? Space doesn't have dimensions. Space is nothing. It's objects that have dimensions. All the mathematicians have put dimensions on the word space. And so that already started wrong in geometry by saying, oh, space has dimension because it's what the block or the solid, the cube, the sphere occupies. So now they get rid of the sphere and they say what we have there is a volume, and that volume is the 3 dimensions of space. So that's how space acquired dimensions, length, width, and height. They incongruously use the word dimension to characterize space when space is absolutely nothing and doesn't have dimensions. It's objects that have dimensions, not the space, the volume, alleged volume that the object occupies. Obviously, there is no volume that the object occupies because the object is not in an ocean. Objects only have relation to each other, and the volume is the object itself. That's why we say position, volume, and the object are all one thing. It's the object itself that the volume it occupies, that is the position, the volume, and the object. It's all 3 in 1. It doesn't displace space like a fish displaces water, in other words. Okay, that's the point I'm trying to make. I'm free to move forwards and backwards, left and right, up and down. Any solid object is 3-dimensional. Is that what 3-dimensional means? That you can move back and forth, up and down, and sideways? No, he's talking about vectors. He's talking about motion. And he never discovered that there's a difference between dimensions, coordinates, and vectors. Dimensions refer to the object, the orientation, how it's positioned, how from the observer's point of view. That's essentially it. So you say, well, or you could even say it from the object's point of view. That's a better way of seeing it. In other words, it's got some kind of corner in there, a vertex, and from there, you can draw 3 perpendicular lines. That's essentially all objects in existence. Any 3D object has that property, that you can, from any location inside it, you can draw 3 perpendicular lines, 3 90-degree lines, one 90-degree to the other. In other words, it's got 3-dimensionality, that adjective called 3-dimension. That's what it is. It tells you that an object is facing or pointing in 3 mutually perpendicular directions. So it's got 2 properties. The first one is direction. That's what a dimension has. And a dimension cannot exist all by itself. So it has to have perpendicularity, orthogonality. Otherwise, it's not a dimension. Okay? And what these people are talking about is what you see at the bottom, number lines. So it doesn't matter to them if they're talking about orientation, location, or motion, because they're going to use the number line. They're interested in number lines. How is a number line different than a dimension, a vector, or a location, or a coordinate? It's different in that it has magnitude and it does not have direction or perpendicularity. Number line doesn't run perpendicular to anything. Time is a number line. Time doesn't run perpendicular to anything. Okay, so time is not a dimension, or a coordinate, or a vector. Time is a number line. Okay, and people confuse and call them dimensions because that's what the mathematicians taught them. Okay, what is a dimension? It's a number of coordinates. What is a coordinate? A number. So what is a dimension? A number of numbers. That's the definition of mathematics today. Number of numbers. And so as long as they use number of numbers, you could be talking, they're not talking qualitatively, so it doesn't matter if you're talking about dimension, coordinate, or vector. They're always talking about number lines. And so he said, we know what that means. No, you don't. Not for the purposes of physics. You may know or understand or use that language in mathematics, but don't bring it into physics. Einstein said space is curved. In what direction do you curve space? Yeah, how do you curve space to begin with, let alone in what direction, right? Space doesn't have direction. Space is nothing. So space cannot have direction or perpendicularity or anything. It doesn't have, it's nothing. It doesn't have shape. That's the point. It's impossible to visualize it. Of course, mathematicians have problems visualizing anything, any of their proposals. They would rather do equations, numbers, variables, constants. You know, they're at home over there. But when you bring them into physics, they get lost completely. That's why there's no such thing as mathematical physics. You either do math or you do physics, one of the two. And if you're going to do math, don't say that you're doing physics. So there is no such thing as mathematical physics, because never the twain shall meet. You know, math is math, physics is physics, never the twain shall meet. Okay, let's move on here. Where does Al-Khalili go with this next? Well, I just wanted to show this, I guess. Let's put it next to, well, I guess it doesn't matter. Let me put it over here. Okay, so what does he say? Dimension. The dimension of an object is the, well, not him. What this is from the Wikipedia. These are the definitions you'll find out there. That's why these guys don't have really a definition of dimension that you can use in physics. Okay, dimension. The dimension of an object is the minimum number of coordinates needed to specify any point within it. What's a coordinate? A bunch of numbers. So what is the dimension? A number of numbers, a bunch of numbers. That's it, the minimum numbers of numbers. That's the definition, okay? Maths, for dictionary.com, the number of coordinates required to locate a point in space. So Al-Khalili apparently never figured out that a dimension is a little different than the coordinate, okay? No, a dimension is not the number of coordinates needed to locate a point within an object, which is what they're saying here. No, that's called a coordinate, not even a coordinate. That's called a number line, okay? Because what they're referring to is the location of a point within, say, a cube or whatever, sphere, from, for example, the edges. So you need to point 3 coordinates, as they call them, downwards, okay, to locate that point. But what are they talking about? They're talking about numbers. They're talking about ordered triplets. Okay, they're saying you need an X, Y, and Z. What? Coordinate? No. Numbers, because it's the number of numbers. So they're saying that to locate a point within a sphere, for example, you got to take one, not coordinate, not vector, not dimension. What you got to take is a number line, right, towards the center. Let's assume it's the center that you're trying to locate. And you take 3 number lines and you say, okay, X, Y, Z, 5, 3, 10, whatever number you want to put in there, okay? And that's the location of that point mathematically. That's what they're saying. They're talking about how many steps the pirate has to take to locate the treasure chest, okay? That's what they're talking about. They're talking about motion. They're talking about numbers. If you have units like meters, how many meters you need to get to that point from here, from there, and from the other place, from 3 mutually perpendicular directions. That's what they're talking about. So yeah, the 4 dimensions of space-time consist of events. Events? What's an event? Event is something that happened, and they're talking about 4 dimensions, and we have something happening, because they're going to use time, and time is a dynamic concept. But see, what we're talking about here, if you're going to use the word point, like location, then you're talking about a cross-section of time. In other words, you're talking like if you cut across the universe, the time, the flow of time, the movie of the universe, the universal movie, and you have a single point, you stop time at that point. So there is no time. Time is 0. And now you can locate, for that point, you can locate, you can locate whatever, you can use your number lines to locate that point and give 3 numbers. Okay, so we're not talking about real, honest to goodness dimensions, coordinates, or vector. We're talking about number lines, quantities, okay? And consist of events that are not absolutely defined spatially and temporally, but rather is known relative to the motion of an observer. Yeah. So you're not talking about dimensions, because dimension is a static concept, whereas motion and time are not. They're dynamic concepts by their very nature. Okay, so they don't have a definition for what a dimension is. That's a big problem already there. And yeah, he ends up with some idiocy here, and this is truly idiocy. Okay, someone discovered this. Okay, it's not always true that every triangle has angles adding up to 180. Oh my God, you learn something new every day. I take all my triangles always had 180 degrees. Always. Every single triangle I've ever seen. And I don't know what kind of triangles they have over there at Cambridge and Surrey University, Surrey. That is only true if you draw a triangle on a flat piece of paper. Oh, where else are you going to draw it? You want to draw it on a wall, my straight wall here, or the blackboard? It's the same thing. Yeah, conceptually, it's got 180 degrees because you're assuming it's on a plane, right? If you draw it on a curved surface, oh, then if you draw it on a curved surface, you don't have a triangle. What you have is a three-dimensional nonsense that they want to call triangle. Euclid there at the bottom, he defined planes in his first book. First 21 definitions of his first book already define what a triangle is. He's talking about plane geometry. So I don't know where these guys got the idea that you can put a triangle on a saddle or on a sphere. But this is what they're going to do. They're going to put it there and they're going to say, ah, see, it doesn't have 180 degrees. Yeah, it doesn't have 180 degrees because you don't have a triangle. And geometry is different when you curve surfaces. No kidding. Yeah, because you entered not in plane geometry. Now you're into solid geometry. Now you have a three-dimensional object. Okay. So yeah, if you put it on a saddle, you put it, is a tri-bar a triangle? Yeah, we're going to say, where is he going to put that? Is he going to roll the tri-bar around? I mean, please bring it out there, and what are they're probably going to draw it on a piece of paper, a plain piece of paper, and fold it over, a sphere or a saddle. Who knows because they play around with all this nonsense that has nothing to do with anything. What does any of this have to do with physics, okay, with science? And they claim to be doing geometry. No, it's geometry. At least you got to stick either with plane geometry or solid geometry. If you go with solids, well, that's a very funny figure that they've got there. So what does he do? Well, he says, and you can generalize this picture from curving a two-dimensional sheet, the surface of the Earth, to curving 3 dimensions. You can? Well, I don't know. He just said we can't even visualize it. But some people obviously try. They have that little triangle there. You've seen the hypercube, you've seen the hypersphere. Well, this is the hypertriangle. It's known as a 5-cell. Okay. Anyways, the surface of the Earth curving to 3 dimensions. But I can't show you a picture of what it means to curve 3 dimensions because our brains are only 3-dimensional. So none of what they propose is visualizable. None of it is imaginable. Okay. You're wasting your time if you're trying to visualize, see it, imagine it. You can't, because he says we're stuck in 3 dimensions. Einstein's theory about gravity is a bit like this, only much more difficult to understand. Mathematically, we can do it, but then you're not understanding because you're not explaining. All you're doing is describing. Okay, and no, that's the word explain and the word understand go together. The word description, I don't know about that. We have to invent new language there for what a description. If you understand the description, did you understand something? Or did you just see what the guy put in there? I mean, when someone tells you, look, a chair has 4 legs and a backrest, etc., you look at it and you say, okay, you kind of, did you understand it or you just visualize it? You say, okay, I visualize what you're saying. You still haven't understood anything because the word understood or understand is wrong to use in that context. Understand, you understand a theory. Description, you just visualize and take it for what it is. Okay, so description, I'm not sure you can use the word understand. If not, we need to clarify those 2 scenarios. Are we understanding a theory or are we understanding a description? Okay. Okay, he moves on and he gets into something that is so famous today. It's been for the last 50 years at least, or 60, I would say now. The Big Bang, okay? General relativity not only explains gravity of why the apple falls on Newton's head, which it doesn't. So he's flat wrong there. I mean, here, this guy's a PhD, And he teaches, I don't know who, I guess masters, candidates for PhDs out there. And what is he saying? He's saying that it explains how an apple falls on Newton's head. Absolutely not. That is not true. And this is not my opinion. It's not true simply because in relativity they make it very plain that you can apply the field equations out there in space. You cannot apply general relativity here on Earth, because if they did, we could get rid of quantum mechanics, the gravity part, because right now quantum mechanics trying to figure out gravity here on Earth, and they can't bring relativity to explain that, because you cannot have a curved space in such a short distance as when you drop a pen. When you drop a pen, it falls straight down, okay? And there's no amount of curvature that you can picture there to try to simulate that. The field equations don't work at that short distance. Field equations need out there, they need to have, you can apply them to Mercury's orbit, for example, or things of that nature, okay? Okay, so he says general relativity gave us the idea. Oh, okay, hold on, I missed one. It explains why the Earth goes around the sun and so on. No, it doesn't. Because the Earth going around the sun, they're saying it's warp time. That's what they're telling you. It's a concept that the Earth, the skin of the Earth rolls around this warp time. Why? Because it's part of that space time that has the depression in the fishnet. That's the analogy that they're going to use. They're going to say, imagine a fishnet, right, curved, and it forms this hole or this depression, right, and a little ball rolls around it like a ball around a roulette. Okay, that's the analogy. That's what you're asked to picture. So what is the physical object, the Earth, the physical Earth, the one that we live in, the one that goes around the sun, the real one? What is it rolling around? And they say it's space-time. That means a warped time with so-called gravity, because there's a mass called the sun pushing it, weighing it down, not upwards, but always downwards. It doesn't weigh it sideways. And so it creates this depression. Fine. That means one of the legs of that four-dimensional space-time is time. They're warping time. Time is a concept, and they're saying the Earth doesn't fly out of the solar system. Why? Because there's a wall of warped time preventing its escape. That's essentially their analogy. That's what they're trying to explain and describe, all of it. And so it doesn't explain why the Earth goes around the sun, because that's black magic. It's surrealistic. You can't even imagine warped time and the Earth coming against this so-called warped wall of time. What is that? What kind of nonsense? What kind of explanation is that? Okay? It describes the structure of the whole universe. I don't know. Structure? Space-time? How can space-time describe structure if space-time is a concept? General relativity gave us the idea that the universe was born in the Big Bang almost 14 billion years ago. There's many other pieces of evidence. Evidence to convince. That's what the priest introduces to convince the flock. Evidence. That's what the prosecutor introduces to convince the jury. Okay? So evidence is used to persuade, convince, recruit, convert, those kinds of things. Was born 14 billion years ago. There's many other pieces of evidence that now tell us that. In all likelihood, overwhelmingly probable. Overwhelmingly probable, I like that. That's how our universe began. Overwhelmingly probable. He's trying to convince you at all costs. He says, yeah, it's overwhelmingly probable. Meaning it's a fact. We can never be sure, of course, in science. No, because in science we are never sure. Surety or certainty or whatever doesn't have anything to do with science. That's atheism. That's religion. Religion is belief, certainty, being knowing. That's religion. That's not science. That's why we can never be sure in science. Absolutely right in that sense. But it tells us how the universe began from a point, from nothing. See, they don't really clarify all these. What do you mean it began from a point? What do you mean by that? There was a point? Who put it there? No, a point meaning nothing. And what was outside of that nothing? More nothing? and evolved and expanded outwards for the structure that we see today. Yeah, so they always end up with this Big Bang point, which nobody can visualize because it's the nothing within nothing. And when that point expanded or exploded or Big Banged, then expanded against nothing. So we have a nothing that's expanding against nothing. That's absolutely great. Okay, we have a problem with his notion, and here's the problem. He says, what happens when a star dies? Which again, it's the same notion as the Big Bang. Black hole, it collapses to a point. Big Bang was a point, so it's all related in that same way. They use the same analogies, the same little rigmarole to try to explain to you these concepts. Okay, what happens when a star dies? Well, a large star supernovas. It becomes a black hole. Okay, a black hole is where a lot of this material of the star has been squeezed so tightly that gravity becomes so powerful that space and time themselves get curved around and closed it off. So he is curving time. Okay, so don't tell me later on that, well, they didn't say that. Yeah, he's curving space and time. He's curving a concept, because you might argue that space is not a concept, that space is a thing that's made of particles. Okay, fine, let's concede that. Let's forget about space. Time is a concept. There's no physical object, standalone object called time. A clock might be true. A clock is not time. A clock is a clock. Time is, if anything, what it measures. Okay, so time, there's no physical standalone object. These people are saying that the concept called gravity, or the concept called mass, is curving time. That's their explanation. That is their physical interpretation. That's why they had to put the fishnet to say, well, assume that fishnet represents space and time. So they are curving time. They're curving a concept. And they're saying the reason the Earth doesn't leave the solar system is this wall of curved space-time, which they obviously represent pictorially with the fishnet. So you figure it out. I mean, am I putting words in their mouth or what? It says, okay, they curve themselves around and close it off, the black hole, right? And just closes it off. Close a piece of our universe off from the rest. Well, how can it close a piece of the universe when it collapses to zero dimensions, zero size, zero nothingness? What has it enclosed itself from if it's nothing itself? How can nothing, absolutely nothing, close itself off from space, which is another nothing, or from the universe? Assume, let's concede the universe is a physical object. Okay, it's a block, it's whatever you want to just imagine, whatever you want to think of it. And here they're saying this star collapses to a point which closes itself off from the rest of the universe. You have a zero-dimensional nothing. It's got no size, no dimensions, no radius, no diameter. It's no nothing. We have absolutely nothing. What is it that has closed itself off from the rest of the universe? If you have nothing, you ended up with nothing. It's called the black hole because not even light can escape from it. I got a big problem with that. I got at least two problems with that statement, okay? And not because of the rope model, but because of what they say, okay? So let's put it in the right perspective, okay? Here it is. And the first one is that the light speed is independent of the source. That's according to the principle of relativity. So we got a little problem here because these people are saying that the black hole affects the speed of light when light is independent of the source. So if the source is matter that fell into a black hole or whatever, I guess a particle that fell into the black hole, it's independent of the motion of that particle. So how do you control light? How do you stop light if light is independent of the source? And you can see there the rocket, the one on the top there, your spaceship. It can go as fast as it wants at the speed of light or close to the speed of light. The light will not be affected. The speed of light will be independent of the motion of that rocket. Then we have an even bigger problem right at the bottom. Light is alleged to have no medium. So what is the black hole grabbing onto when it slows down light trying to leave the black hole or the surface of the black hole or whatever? So what is the black hole pulling on or obstructing or blocking? Okay, how do you pull on nothing? If it has no medium, what is the black hole pulling on? This is a serious problem. These two are fatal to the notion of a black hole. Okay. Okay, let's continue here. Here it goes. Okay, Einstein didn't believe in black holes. He says that, okay, not me, okay? And yeah, Einstein did not believe, and his theory of relativity predicted their existence. So even though his theory really was applied by, was it Schwarzschild? In 1915, he applied Einstein's equation to the black hole, to a star that was more massive than the sun. He came up with this notion of black hole. Okay, and it was later on called black hole. He didn't call it black hole. They talked about singularities and zero size, etc., for many years. Okay, and in 1970, astronomers saw. Look at that word, saw. Okay, eyes out in space and understood that their behavior was exactly as predicted by Einstein's theory. What did they see? Well, a Canadian fellow known by Tom Bolton, he was, I guess, the first one he was observing stars out there, and he says, okay, there we have Cygnus X1, and this is a star system there, or they look at it as a star system, where they say, look, there's a star revolving. Uh-oh, I got cut off. I think I'm being reconnected. Hopefully I'm reconnected fine. You have this star rolling around nothing, okay? And so they assume, see, that's what more or less what they saw. They studied that for a while. It didn't go that fast. But they say, this star is moving. It's moving in circles. It's moving around nothing. There's got to be a mass in the center of that orbit. And that's how they proved the existence of the black hole in the 1970s, okay? So did they ever see the ghost? No, it's like, what moved my curtain? Well, I think it was my great-grandmother's spirit that moved it. Did you see your great-grandmother's spirit? No, I didn't see her, but what else could it be? Well, maybe it was the air, flowing through the window, I mean, I don't know why the curtain moved. No, it's got to be my great-grandmother's spirit. I know. It was her birthday, and she came to visit me. So that's how they determine these things, indirectly. Keep that in mind. There's no proof or evidence or anything. What they see is something moving. They say, what else can it be except a hidden mass? And they say for this star to move that fast around nothing, it's got to be a mass that weighs so much. And so they calculate the mass. According to the equations, they say it's got to be enormous. And so they say it's enormous. It's in there in the center of this orbit, and they call that a black hole. And they call that inexistent mass a black hole. And yeah, we do it a little differently in rational science. I'm not going to get into that right now, but if you ask the question, I will address it. Okay. No one knows what's inside a black hole. No kid, because we're cut off from this thing that disappeared, right? A zero-dimensional nothing, right? Like the afterlife. When you go to the afterlife, you can't come back and tell people. Yeah, no kidding. And I guess that's why the black hole is appealing to a lot of religious folk, traditional religions, because they say, hey, essentially you've proved what we've always known all along, that there is a heaven. We call that heaven the black hole. And you took it from us. You borrowed that concept. And so the soul, when you die, you go up there to heaven, and it's like going to the black hole because you never come back. So a lot of these notions are from traditional religions, and they extrapolated them into so-called science, mathematical physics. If you were to go into a black hole, what would happen? Well, you would be spaghettified, like you see the poor astronaut falling in there at the bottom. One possibility is that you squash down to a singularity. What is a singularity? A point at the center. A point of zero size and infinite density. What is the size? Zero size. A lot of these people, I had a lot of people tell me, no, that's not what the mathematicians say, that it's zero size. A singularity is zero size, no diameter, no radius, no nothing, zero dimensions. So I don't know how to get that point across. That is what these people are saying. Al-Khalili says it, because you need more evidence. Let's put more evidence. Here we have Stephen Hawking, okay? I'm not going to read it all, but here you can see a little snippet. Eddington was shocked by the implication, and he refused to believe Chandrasekhar's result, who published a paper on this subject, right? Eddington thought it was simply not possible that a star could collapse to a point. Einstein himself wrote a paper in which he claimed the stars would not shrink to zero size. And at the bottom you'll see Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. That's what they gave him the Nobel Prize for. Okay, so people should read more and talk less nonsense. Yes, but what the mathematicians are saying is zero size. A black hole is zero size. It's nothing, absolutely nothing, with infinite density. Why is it infinite? Because it's got no volume. That's why it's infinite density. Okay, and just in case, we got two more testimonies here. Okay. Just at random, I have a lot more testimony. I pulled two out of there on solving the equation with a particular value of central density. You will get a model of a star with mass m and radius r. Plot r as a function of m and show that r falls to zero when m is equal to the Chandrasekhar mass. What is r? The radius. What is the radius? Zero. Okay, when it reaches the Chandrasekhar mass. Did you understand? Black hole is zero dimensional. Okay, if the mass of the star is greater than about 3 solar masses, it goes through the neutron star stage and keeps collapsing. In this case, the gravitational attraction is so intense that neutrons are literally crushed out of existence. We call the object a black hole. What is a black hole? We crushed all matter out of existence. There is nothing there anymore. So please don't tell me that a black hole is not zero dimensional. Everybody who's out there who's won a Nobel Prize has said it, so don't change that around. Black hole is 0D. Okay, I know it destroys your religion, your beliefs. You had this great idea about the mathematical physicists. That's what they're saying. They're saying the star collapsed to nothing, but it's got infinite density. Why? Because it's got zero volume, zero dimensions. Okay, okay. Little alkali. Alkali, he continues, so we know everything about black holes from mathematics of Einstein and from observations of the outside of a black hole. What a black hole does to the material around it, sucking it in. Yeah, it crushes all material out of existence. That's what we know. Okay, so, I mean, why would it stop? If you've got an enormous mass, the enormous, the most massive object you can imagine, it's many times more massive than our sun. It should collapse, 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 collapse until all structure is crushed out of existence. Why would there be structure left over? Okay, that's what you got to answer. Okay, we now also understand that most galaxies have a supermassive black hole at its center. And there you have a galaxy. All galaxies have a black hole. Okay, that eats stars for breakfast, and you got to eat your what is it? Your Cheerios, or what was it? The Lucky Charms. They have all these little stars. You eat them for breakfast. Any star that gets too close to this black hole in the center of our galaxy will get swallowed up, and the black hole grows. How can a black hole grow if it's zero dimensional? What is it that grows? The infinite density, is that what grows? The amount of mass grows infinitely. What is it that grows? You know, and where is the matter falling into if there's nothing there anymore? I mean, you got zero dimensional nothing, zero radius. What is the star that comes close to the so-called black hole? What is it falling into if there's nothing there? It goes all the way to the singularity. When it gets there, say, oh, I thought I was hoping to see the Wizard of Oz here, and it turns out, you know, it's Dorothy. You know, there's nothing there. Not even Toto survived. Okay, and from there, good old Al-Khalili keeps going. He turns it into this contraption known today as a wormhole. He gets this from the Einstein-Rosen bridge. I'll get to that in a second. Another option with a black hole is a bridge. It's a tunnel to somewhere else. Oh, this is where you get. This is the point where you got to get your beer. Okay. It's a tunnel to somewhere else, either within our own universe or, if parallel universes exist, into a parallel universe. Okay. Nowadays, physicists are very convinced by the evidence that black holes exist. But what is inside a black hole, whether there is a tunnel or a route to somewhere else, is complete speculation. It's allowed by the mathematics, but we don't know how true it is. Again, talking about true is what your opinion is. What is true to you is false to your neighbor. Okay. What wonderful, what's wonderful about this idea of a tunnel is that it could allow for us to build a time machine. You see where he's going with this. We haven't proved it. We don't know. It's allowed by the mathematics. And so maybe, just maybe, we can build a time machine. And that gives everybody hope that they can travel to the future and meet their, their great-grandsons. Okay, here's where they got this. This was Einstein-Rosen paper of 1935. And I'll just read that, what's in close there. The many particle system is expected to be represented by a regular solution of the field equations corresponding to a space of two identical sheets joined by many bridges. Okay, that's where the Einstein-Rosen bridge alias the wormhole came from. And there was a lot of debate in 1935 and 1936. People like Oppenheimer, they wrote a lot of, the other one was Chandrasekhar himself. All these people wrote papers about black holes. It was a big topic in 1935, 1936. They just said, well, yeah, it's speculative. Some people believe they exist, some they did not, and Einstein was one that did not. But I like what he writes in his paper, and I just pulled this out. For these reasons, writers have occasionally noted the possibility that material particles might be considered as singularities of the field. This point of view, however, we cannot accept at all, for a singularity brings so much arbitrariness into the theory that it actually nullifies its laws. So from a mathematical point of view, good old Einstein, he was against the black hole as a real entity, and he made it plain in that paper. Okay, so if you're looking for evidence, go to the source, say, hey, Einstein said this, here it was. He never believed in black holes until his death, 1955. He never believed in that. So if you need authority, use Einstein against the black hole. Okay, because a lot of people out there say, well, Einstein, they don't say he proved it or he believed it. They say, thanks to Einstein we have the black hole. That's how they put it. They give him credit like, our master told us, No, Einstein was against black holes. He was against Big Bang. He was against gravity waves. He was against all that stuff. He wrote about it, all of them, but he was against them. Okay, just so you know. He didn't believe in them. He didn't think they were real. He thought it was just a mathematical, exercise. That's all it was. He didn't put it beyond that. He didn't think it was physically possible. So here you have two universes, parallel universes. Do they really exist? Is there such a monster out there? Well, if they share the same space, well, then you don't have two universes. It's one universe with, I hope I'm still online. Let me check real quick. Oh, yeah, I'm online because I was cut off a minute ago. So I was, give me a second here. Let me get back into the ball game. Okay, so is there such a thing as a parallel universe? Are there two universes out there? Well, if they share the same space, if the space in both of them is the same, all this matter is in the same space, so to speak, because space is nothing. So there is no division between these two universes, and so it's ridiculous to try to put, let me get this. I got the wrong one. Where is it? I lost it. Well, anyways, here it is. See, it's ridiculous to put a wormhole between those two because what is the wormhole traversing? Okay, what is it going through if we have a single space and space is nothing? See, for this you have to define what space is because these people are saying we're going to make a hole through space. Well, how do you make a hole through nothing? That's what these people are saying. That if you have a black hole on one end, a white hole on the other, for example, well, then you can go through this bridge if you can get through that one-dimensional skinny tunnel. Okay, that's what they're saying. Okay, but if they share the same, the matter on one side, on the right side, is the same, is a different matter than the one on the left side, like two galaxies, for example, and they share the same space. In other words, there is no difference in the space between them. Then we have a single universe. There is no parallel universe. The only way you can conceive of a parallel universe is the way I said in the other day, that you have two universes and the matter over here is interconnected by ropes, but none of the matter here is interconnected to the ropes of the universe over there. Okay, so that's why they're isolated, because they're not connected by ropes. For example, you could say that the Andromeda galaxy is an island universe. Okay, you can't say that in the rope model. Why? Because Andromeda galaxy is connected to us physically through the ropes. Why? Because light comes through the ropes. That's how we can see the Andromeda galaxy under the rope model. Okay? But then, the only way we would not see the Andromeda galaxy, for example, if someone cuts the ropes, which is impossible, but we will assume here. If God came in there with his magic scissors and cut the ropes, yeah, then you would not see it, because the signal has to travel through the ropes to your eye. Okay, we wouldn't even feel the gravity, because again, the only reason we feel gravity is we're physically connected to the Andromeda galaxy. The only way you can consider the Milky Way and the Andromeda galaxy as two separate universes if they're not connected. And that's the only way. Otherwise, what are these people talking about parallel universes if they all occupy the same space? It's like saying that the Andromeda galaxy is a different universe. No, it's a galaxy. That's what it is. And if you have a bunch of matter over there, well, are you going to call that a different universe? No, the universe is all of it, space and all the matter within it. And if we all occupy, to use that word, if we're all within the same space, to use that term, then all we're saying is that that's the universe. Space and matter. That's it. Matter and space. That's the universe. And anything within that, how are you going to isolate it and say, oh, that's a different universe? So you can't do that, because it's a question of language. I guess it's this one. Okay, so now, yeah. And he goes in there and he says, this is what we call a wormhole, okay? It allows us to have a shortcut through space. So they're cheating again. They're saying, look, we're bending space and we're going through space to get to the other space. What kind of nonsense is that? It allows us to have a shortcut through space. Imagine you want to get from our galaxy, the Milky Way, to another galaxy very far away. You would think that the shortest route is a straight line. Yeah, that's the way we always understood a straight line. Straight line. I want to get from A to B. You go through a straight line. That's the shortest path. They're saying, no. What you do is you curve around. I thought a curve was already a longer path. Yeah, so what they do, they artificially put the galaxy on top of each other and say, well, instead of going from here to there straight, what you're going to do is bend the galaxy over your head, and now you can go a straight line and beat the speed of light. The light doesn't go straight from here to there. Light has to go all around, but you can go straight and beat light. You understood that? The galaxy's over there. I can see it's over there. But these people say, no, you take this curve, and this curve puts the galaxy on top of your head. So this curve through the fourth dimension is really a straight line in our dimension, in our 3 dimension. So you're going in a straight line from this galaxy to that galaxy, but light has to go through the curve. Light doesn't go straight. Light has to go through the curve because you're beating the speed of light. If it takes light from Andromeda galaxy to reach us 2.2 million years, because it's 2.2 million light years away, that means traveling at the speed of light, it would take light to reach us 2.2 million years. What they're saying, oh, we can take a shortcut. We can beat light. We don't travel faster than light. We just change the itinerary. Instead of going like light does, taking that long curve around the fourth dimension, time. No, we cut across and we just go straight because it's the path through the fourth dimension. This is what these people are saying. Well, not if your Einstein theory of relativity, okay, if you use it, right? Because Einstein's relativity tells us that we can bend space with gravity. So the shortest route from A to B is not a straight line. It is only a straight line if you stick to our space. But if you could bend it over your head, like if you could curve it so that A folds like a sheet of paper, A on top of B, there's a route that allows you to jump from A to B in a shorter distance. That's the idea of a wormhole. In other words, you beat the speed of light, not because you travel faster than light, but while light is dumb and takes the long route from here to Andromeda, you put Andromeda on top of your head and you go in a straight line. That's what they're saying. Okay, great. And what I like is his evaluation of that. Okay, here it goes. Okay, this is his evaluation, not mine. Okay, and he says the following. He says, Alice in Wonderland is a wonderful example of an Einstein-Rosen bridge. Alice chases the white rabbit down an Einstein-Rosen bridge to a parallel universe. Okay, yeah, I think this is Alice in Wonderland physics. Alice's looking glass. She's going through a wormhole into a parallel reality. My God. Yeah, a wormhole is equal to the rabbit hole. So don't fall in it because who knows where you're going to land. Okay, so to rub it in, Al-Khalili has introduced some authority. He's got to pad it somehow so that you believe him, because the issue is not for him to explain something so that you understand it. The issue is to get you to believe in his religion. Like the pastor, like the priest. They go to church, and they talk and they say, you have to believe because the Lord said and the Bible says, and, and they'll read passages and say, are you going to deny the Archangel Michael or whoever, right? And so they use statements of authority to get their point across. And here's one of the most famous statements from this fellow. He says, Einstein's theory of relativity have passed every test possible to check whether they're correct or not. Correct? Correct according to whom? To him. He believes it, so it's correct for him. It's right for him. It's truth for him. It's like the guy who believes in God and says, look, it's truth to me. It's correct. It's right. So it's an opinion. Correct is an opinion. Okay? And he says they're checking it. Checking what? What are you going to check? All you got to do is look at the mechanism. If the mechanism is rational, it belongs to science. If it's not rational, it doesn't belong to science. We don't care if it's correct, accurate, precise, right, truth. We don't care about it because that's your opinion. It's truth to you. So see, this is how they introduce this influence to try to get you to believe, not to try to understand, but to believe. They say, we don't understand, but please believe what we don't understand. And believe me, physicists would love to be able to find a fault or flaw in Einstein's theory of relativity because there's a Nobel Prize for you, okay? So yeah, they go with these little coins, these beauty contests, and they say, look, walking down the aisle with their bouquet and saying, oh, I'm the queen of the world. I'm the most beautiful woman in the world. These guys saying the same thing. Oh, I'm the most intelligent guy. I was honored with a bouquet of roses or a medal, I think they're Olympians or something, My God, what the world has become. And just in case, he throws in this little bit. He's got to throw this thing in there. Also, he says, we're not here to propagate or maintain a dogma. Although many people will say that that's what science does. Actually, the scientific method is always self-testing, always checking. And if something comes up, an experiment, a result that shows a theory has a flaw, that theory is dead. It's killed. A theory is an explanation. It's objective. So you don't believe or don't believe in a theory in science. That's religion, whether you believe in it or not, or whether it's right or wrong, or whether you proved it or not, or tested it, or ran an experiment. That's all belief. A theory has to be objective, so that's the same for every human on Earth. You watched the movie of the mechanism. You watch the rock breaking the window, and we all see the same thing. We saw the rock breaking the window. That's the mechanism. We're done with science. Now, if you believe something else, you say, well, I don't think that's how it happened. I think it was a crowbar, or I think it was a baseball, a horseshoe. Fine. But that explanation, the one you just saw, is the same for everybody on Earth. It's objective. What we all saw is a rock going through the window. Whether you believe that it was a rock and you think it was something else, that's a separate issue. You have a different theory, fine. But that one, we all agree on. We're all on the same page because we all saw the same thing. This is not what these guys have. They talk about dogma and they say, well, it's not dogma. We prove it. We ran tests. We verified. What did you verify? You're talking about invisible things, and you're talking about space-time, which is a concept that you can bend. What have you proven? What have you verified? What kind of experiment did you run to prove nothing? The warping of nothing. Yeah? Okay, and so the fact that Einstein's theory of relativity has survived for a century, again, authority, okay, gives us confidence, mathematical physics. Confidence is an opinion, that they are telling us something profound and correct about reality. Reality? Well, what does space-time have to do with reality? Four-dimensional space-time. They say they can't imagine it, so they can't imagine their reality? They can't imagine their explanation, the mechanism they're going to propose? They tell us that time travel to the future is possible. So that's what they tell us. Okay, that's what all this nonsense tells us. Okay, what's Al-Khalili's conclusion, closing argument on this? That's a lot of fun. Okay, so if you waited for the end, here's the ending. Okay, the punchline. Science is all about magic and mystery. It's all about unknown and testing the unknown. Talking about, I guess, magicians, astrology. I don't know what he's talking about anymore. Okay, magic, is that what it's all about? The unknown? I thought it was about the known. So here are my summary and conclusions. Okay. First one, Al-Khalili starts his presentation by stating, today we're going to find out that fiction is actually science fact. My God, what a way to start a presentation of science. He introduces 4D space-time and states that gravity is 3D warped space warped into the fourth dimension. He clarifies that such monster is unimaginable. He doesn't understand the concept of dimension. He never learned that triangles are planes, 2D, right? Euclid showed that in the first book of his Elements, right? Concludes that matter self-created from nothing, known as creationism without God, okay? Black hole collapses to 0D size but has mass without matter. Says that wormholes, tunnels through space, are predicted by math, even though space is nothing. So how can you build a tunnel through nothing, especially a one-dimensional tunnel? Okay, admits that wormholes are alive. Down the rabbit. Alice. I meant to say there. Our Alice down the rabbit hole type of stuff. And science is about doing magic and irrationality. Okay, so those are my conclusions of Al-Khalili's presentation lecture. All nonsense, absolute poppycock from beginning to end. None of that survives. So whatever he learned, whatever he teaches, whatever he did throughout his life is absolute nonsense. None of it survives in rational science. Science, we have to have rational explanations that we can visualize, not to believe, but to understand the mechanism. You have to make it objective so that every person on Earth, except the blind guy, sees the same thing on the screen. Okay? That's how it is.